Hey, everybody. It's Wednesday, April 7th. And as you can see here in the aim today, our goal for today's video is to talk about how we can apply conservation of energy to a spring block oscillator experiencing simple harmonic motion. Now, obviously, there are a lot of things that we can say about conservation of energy and try to apply it to systems where there are springs and objects attached to those springs. This is actually something we did quite a bit when we were talking about conservation of energy in general. But when we're going to try to apply conservation of energy specifically to a spring block oscillator, I think this is going to become a lot easier to understand if we actually just look at it and observe some things about the system. So let's go ahead and take a look at a simulator that will allow us to observe the motion of a spring block oscillator experiencing simple harmonic motion. So the first thing you want to pay attention to here as we're going through and making these observations is that every single thing we are trying to do here is to ascertain what the energy analysis is going to look like. So to start us off, I'd like everybody to look at this 100-gram mass, this 0.1 kilogram mass attached to this spring. What can you say about its energy right now? The thing that you should be thinking of as far as what we can say about the energy of this thing right now is that it has no energy. If we want this thing to have energy, we've got to give it some energy. Or in other words, we have to change its energy. Now, the obvious question here is how can we change the energy of an object? And what I hope is that when you all just heard me say, how can you change the energy? The first thing that you thought about was work. In order to change the energy of an object or a system, you have to do work on that object or system. And so the key idea here is that if you are considering this from an experimental standpoint, when you set this thing up, it has no energy. And if you want to give it energy, you have to do work. Now, of course, the obvious question is, well, how do we do work in general? Well, in order to do work in general, you have to apply a force over some displacement. And so what I'm going to do here is I'm going to apply a force downward, and the block and the spring, the block spring system, is going to be displaced downward. Then when I let it go, you can clearly see that I've given the thing energy from doing work in that way because now the thing is moving. All right, that's point number one. One of the real reasons why I wanted to show you this is because this simulator allows this movable line, and this movable line is going to help us make a point. Notice here that when this black line, notice this black line here is the equilibrium position. When the object is moved from this black line, it will start to oscillate. And the important thing that I want to try to convince you of here is that when you move the object a certain distance, when you are doing work on it, and you let it go, notice where the object is returning to each and every time it is bouncing back and forth. Notice here what I did was I moved the block to exactly where the red line was in the middle of that 100-gram marking on the block, and the object keeps going back to that point. To put it another way, when the object keeps bouncing back and forth, its maximum displacement from the equilibrium position is that distance I pulled it back to. Now, if you don't quite follow what I'm saying, then let's show it again. Now I'm going to move the line down to here. Notice the equilibrium line is exactly at the center of that 100 grams. I'm going to pull the 100 grams exactly to the center of this red line. And notice the farthest it's ever going to get from its equilibrium position is going to be the place where I pulled it down to. It's very important to remember when we are talking about a spring block oscillator or an object experiencing simple harmonic motion, that what we are saying is that when we're talking about the maximum displacement from the equilibrium position, we're talking about the amplitude. And this is what I meant when I first was introducing this video before I pulled up the simulator. Yes, we can obviously apply a lot of information we've learned about conservation of energy to systems with springs in general. But in the last couple of days, really the last couple of weeks, if you count the break, we've learned a lot about the particulars of simple harmonic motion. And so the key idea here is that we want to also keep in mind how conservation of energy is going to inform how this thing is going to move, keeping in mind that stuff we've already said about simple harmonic motion. A big point here is that in order to give this system energy, you have to do work on it. And when you do work on that system, by pulling the spring down a certain distance, you are deciding what the amplitude is. The amount of distance this spring is stretched in the very beginning in order to give the system energy will ultimately determine the amplitude of the oscillations for the rest of the time the thing is oscillating for. That, I do believe, is an extremely important point in understanding the energy analysis for simple harmonic motion. And so that's actually the first thing I want to write down. During the work period, and by period here, I don't mean like period of simple harmonic motion. I mean the period of time in which you are doing the work. During the work period, the distance you pull the spring is the new amplitude of oscillation of the spring block system. That means when you are doing an experiment, you are the one who decides how much energy the system has, because you are the person who decides how much work to do. And if you're deciding how much work you're going to do by pulling the spring down a certain amount, then ultimately you are deciding the amplitude of the oscillation. That's a very important idea here, because when it comes to experimental design questions on the AP test, a lot of what I've noticed over the years that kids ask is like, well, how do we know how much energy the thing is going to have? You don't. You determine it yourself. And because the amplitude is literally determined just by how far you pull something, it's not rocket science to figure out what that is. You just measure it with like a meter stick. Oh, I pulled it down 10 centimeters. Notice you can actually do that in the simulator here. There's a ruler that you can go and drag over and say, okay, well, the equilibrium line was at 0 here. And so that means, oh, now I moved it. But that means the amplitude I gave the thing was, about 19 centimeters. Now, obviously, if you were doing an experiment, you would make it a number less disgusting than 19 centimeters. You'd probably just move it to 20. But that's the point. This information here on this slide is extremely important to understanding everything we're going to say for the rest of this video. So take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, I want to go back to the simulator here so we could observe it a little more. And I'm going to get this ruler out of here. And let's just reset it. Now, I'm going to pull this thing down to here. And so I want you to watch very carefully what's happening. This thing has no energy. I'm going to exert a force over a displacement. And now I've given the thing energy. But notice, I'm no longer exerting that force over that displacement. Like, that part is over. I didn't let it go yet, but I'm not doing any more work. I am still exerting the force, like here with my mouse. But hopefully you get the idea here. I'm not exerting that force over a displacement anymore. So I'm no longer doing work in a physical sense. I just moved it by accident there if you're watching the screen very carefully. And so the question, again, there too, the question we have to ask here is, what happened? I did work, and supposedly by doing work, I changed the energy of the system. But how? What happened to the energy of the system? Now, if what you're thinking is, well, the energy increased, how did it increase? How do we know? What kind of energy changed? The important thing that you need to realize here is that the energy of the system just changed in a way that you can tell very easily, because look at what happened to the spring. It was like this. Now it's like this. It was like this. Now it's like this. The idea is the spring stretched. And because the spring stretched here, we now know that this energy, once I did the work on the system and did that work over that displacement and gave this thing energy, that energy is manifesting itself as elastic potential energy. How do we know? Because the spring got stretched. Now, of course, once I let this thing go, it's not really like a special kind of simple harmonic motion problem. It's a good old-fashioned conservation of energy problem. I'm going to let the thing go. What starts happening to the mass? It starts moving. So it turns into kinetic energy. Then notice here on the upswing, it goes and compresses the spring, and the object stops. And so the key point here is that now that we've established that once you do that work, that spring stretches and that energy turns into elastic potential energy, we can talk about the energy here in extremely simple terms. Notice here I've stretched the spring. There's elastic potential energy. I release the object and it starts moving. It turns into kinetic energy. Now it compresses the spring. We have elastic potential energy again. And this thing is just going to cycle back and forth between elastic potential energy and kinetic energy. And so the key point here is we can talk about the energy analysis in remarkably simple terms. Now, we're going to start out by talking about this for a horizontal spring block oscillator. This simulator has a vertical spring block oscillator. And so as you can see, which we'll get to eventually, that this thing has gravitational potential energy at play, which is going to lower and increase as we continue to move this thing up or down. But because we're going to do this for a horizontal object, basically it's the same thing, just without considering the effects of gravity. And so what I'm actually going to do is I'm just going to slide this thing down to make there be no gravity, essentially, and we'll just do the analysis like that. So notice here, this thing has no initial energy. That's what we said. In order to give it energy, we have to do work. Notice here, when we pull this thing down, the elastic energy increases. So that work that we do initially manifests itself as elastic potential energy in the system. And then when we let it go, that energy just cycles back and forth between elastic potential energy and kinetic energy. And that's it. It just cycles back and forth between elastic potential energy and kinetic energy. And that ultimately is going to be the basis for our conservation of energy analysis. Now, before we get to discussing the equations, I'd like to write down a couple of very important things about what we just said. The first one is that in order to give an oscillator energy, we must do work on it, which first appears in the system as elastic potential energy. That's important. And that elastic potential energy that this thing has is the energy that it has. It really is the elastic potential energy at the amplitude. And that'll be an important point you'll see when we get into the math. The second thing we can say is the amplitude of the oscillation, of course, that's a really important part, is determined by the amount the spring is stretched during the initial period of work. It should be clear to everybody then that this will also affect the amount of potential energy stored in the system, because how far we pull it ultimately determines how much the spring is stretched, which obviously determines the amount of elastic potential energy. That's the whole thing. US is equal to 1/2 kx squared, so it gets exponentially bigger the more and more we pull the spring. And lastly, here we can say what we've already discussed. After the spring is released, there will be a continuous conversion between elastic potential energy and kinetic energy. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So what I'd like to do here now is do the derivation for the equations that we're going to be using here for conservation of energy. Now, despite the fact that you may or may not realize this, is actually super annoying to do long derivations on the computer with this digital sketchpad thing that I have here. And so what I'm going to do is I'm going to bust out the old whiteboard and do the derivation on there, just because it's going to be a heck of a lot easier for me to do. I will pop back and forth now here in the next 20 to 25 minutes between the whiteboard and the PowerPoint, but it's going to be much easier for me to do it this way. And so hopefully you will find no loss in quality between what you're going to see on the board and what you would ordinarily see on the screen. Let's take a look at how we can derive some equations using conservation of energy for a spring block oscillator. So it should be obvious to everybody that because we're talking about conservation of energy and applying conservation of energy to the simple harmonic oscillator, the spring block oscillator, that the premise from which we're going to operate is going to be this one, that the initial total energy is equal to the final total energy. Now, as we just said a minute ago, and I'll write this down over here, the initial total energy in the system is going to be equal to that work that you put into the system. And I'll just write here the work put into the system. So I can rewrite this part as work in. And as we said, that initial energy, once the block is released, it's just going to cycle back and forth between elastic potential energy and kinetic energy. So I can write this. And that's the basic statement of conservation of energy for this kind of problem. Now, ultimately, what we should do is we should try to solve for something that can be solved for. I understand that that seemed a little dopey, but let's write some stuff down first, and then I think it'll be clearer to you. First, the amount of work that you put in manifests itself as elastic potential energy, which gets the equation 1/2 kx squared. But as we said, since the amount you stretch the spring in the beginning is the amplitude of the oscillation, we're going to write this term not as 1/2 kx squared, but as 1/2 ka squared, because that x, the distance you stretch the string from the distance you stretch the spring, that's harder to say than it seems. The distance you stretch the spring from the equilibrium position is the amplitude of the oscillation there, so we're just going to call that A. And then at any point, the elastic potential energy this thing has is going to be given by the equation 1/2 kx squared. So essentially, this is a function of how far away it is at any given moment from the equilibrium position. And then, obviously, plus 1/2 mv squared. So perhaps we should just put that in a box first, because that ultimately will be the main conservation of energy equation. But we would like to, clean that up a little bit, maybe simplify, maybe recognize a couple of things. So the first thing that should be noticed is this is a constant. This is going to be a constant. Now, obviously, it's going to change from problem to problem, but once you stretch that spring and you set the thing in motion, the amplitude is a set number. Obviously, this is a constant, as we just said. The mass is a constant. The only things that are possibly going to be changing here are x and v. And so let's just say this was the equilibrium position. You pulled it down to here. Now it's moving back and forth. Obviously, wherever we choose to stop it, like let's say here, the x value is set if that's where we decide to look at it. So the point that we're trying to make here is that the speed that this thing has is a function of the position. If we choose to look at it here, the x is 0, and the speed will be determined by the fact that the x is 0. If we choose to look at it here or here, you get the idea. So what we're going to do is we're going to go ahead and solve this for the speed, because as we mentioned, the speed is a function of the position. And so the first thing I'm going to want to do when solving this for the speed, just to make things easier, is get rid of these halves. And so I have ka squared equals kx squared plus mv squared. And if I want to solve this for v, I want to leave that on the left-hand side just for my own sanity. And notice I'm writing the equal sign. If I'm going to solve this for mv squared, I have to subtract the kx squared over. So I have ka squared minus kx squared on the other side of the equation. Okay, what do you think I can do with this? Well, I don't really feel like plugging in k twice, so I'll factor that out. I have mv squared equals k times a squared minus x squared. I want you to take a moment to realize why this makes sense. X can never be bigger than a. So either this term is going to be 0 or it's going to be bigger than 0. If x equals a, when it's at the amplitudes, then it's 0. When x equals 0, it will just be the amplitude. But the biggest number x can be is a value that's equal to the amplitude, because it's not going to go past the amplitude. The amplitude is the maximum displacement from the equilibrium position. So this is never going to be negative. It works. And then lastly, to solve this for the speed, I got to divide by m and take the square root. You guys are good at math, so I'm going to kill two birds with one stone here. And I have k times a squared minus x squared all over m. And that's all under the radical. So there's my equation for the speed. So I want to take a moment to discuss a few key relationships there But first, before we do that, I think it would be important for us to just go through and define the terms in the equations we just looked at before we get carried away. So the first thing that we should say is obviously, as you saw in that equation, we started by setting the initial energy equal to the final energy. We said, of course, we can rewrite that by saying the work we put into the system is equal to the elastic potential plus the kinetic energy. And then we end up with the equation 1/2 Ka squared equals 1/2 kx squared plus 1/2 mv squared. Now, you already wrote that down in your notes, so you don't need to go nuts about that. But I do want to just be clear about defining these terms. K is the spring constant, measured in units of newtons per meter. A is the amplitude, measured in meters. X is the displacement from the equilibrium position, also measured in meters. V is the speed of the object, measured in meters per second. And, of course, M is going to be the mass of the object here, measured in kilograms. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, of course, the whole point of deriving that equation was to get an equation for the speed of the object. And so if we want to look at the equation for the speed of the object, as you saw, we get the square root of k times a squared minus x squared over m. And let's just be clear, k is the spring constant, a is the amplitude, x is the displacement from the equilibrium position, v is the speed of the object, and m is the mass of the object. Just make sure you have all those things straight. Of course, k is measured in units of newtons per meter. The amplitude and the displacement from the equilibrium position are measured in meters. Speed, of course, is measured in meters per second. And m is the mass of the object measured in kilograms. Of course, if you actually put these units together here, looking at this equation, you'll see it does, in fact, give you units of meters per second, because we have newtons per meter times a squared minus x squared is going to give us units of meters squared. And then we're going to divide that by kilograms. So, of course, when we do the numerator here, we're going to get Newton meters per kilogram. And, of course, a Newton is a kilogram meter per second squared. We multiply that by a meter and divide it by a kilogram. The kilograms cancel. We get the square root of meters squared per second squared. And, of course, that ends up giving us just meters per second. Take a second to pause this video here and write that down. When you hit play, we'll move on. Now let's take a second to make sense of a few important relationships. First, V is proportional to root K. That makes a lot of sense. Why? In magnitude, at least, the force is proportional to K. So for the same stretch, a bigger K means a bigger force. And if there's a bigger average force, and why I say average is because the force changes, right? Because when the stretch is big, the force is big. When the stretch is small, the force is small. When the K is bigger, the average force gets bigger, or at least the maximum force gets bigger. And so it would make sense that a bigger force is going to cause a bigger acceleration, and that's going to end up making the thing have a bigger speed. Okay, cool. Also, the speed is inversely proportional to the square root of the mass. In my view, that makes a hell of a lot of sense too, because a heavier object, or I should say an object with more mass, a more massive object, has more inertia, and thus is harder to move. Okay. So a bigger mass would give us a smaller speed. All right, fine. Last thing is about this a squared minus x squared business. At the amplitude, when x equals a, I want you to think about what happens to the thing. Notice at the amplitude, it stops and then turns around. This equation shows us that, because notice if we plug in that x is equal to a, we get a squared minus a squared. And a squared minus a squared is 0. And so that would show us we have a 0 speed. What it also shows us, I think, which is super important, is when x is 0, you have a minus 0, meaning the biggest that this term in parentheses can possibly be is when x equals 0. And what that tells us is when the object is at its equilibrium position, that's when it's moving fastest. Now, that's something you probably already realized, maybe, on your own, when you were looking at those graphs in the beginning, because the slope of the tangent line is getting steeper and steeper and steeper and steeper until it gets to the equilibrium position. So the equilibrium position is where the object is going the fastest. And so what we would like to do is we would like to get an equation for the max speed. So we're going to go ahead and do that now. If you did not get a chance to write this down, I highly suggest you pause the video and do that. And before I erase this, come on, you got to give that to me. That's a pretty damn good sine curve. I think we could all agree. All right. So we'll put this under the heading max speed, I guess. And I want to just leave this here for a second as a reminder. So right here, the maximum speed we're going to get from this equation. So first, we should say the maximum speed occurs when x equals 0. And so when x equals 0, we just have v is equal to the square root of k times a squared minus 0 over m. Now, obviously, that's kind of a stupid waste of a step, but the point is what we get is k over m times a squared under the radical. And since the a is squared and it's under a radical, we could pull that out and say that the maximum speed is root k over m times a. I hope there's something about that equation that looks a little familiar to you. That square root of k over m. What is that? Oh yeah, frequency equation. That's weird. Notice I can solve that for k over m. Sorry, solve that for root k over m by multiplying both sides by 2 pi. And if you remember, going back to the AP reference table, 2 pi times the frequency is the definition of omega. So we can actually rewrite that as omega times a. Let's take a second to define these terms here. K is the spring constant in newtons per meter. M is the mass measured in kilograms. A is the amplitude measured in meters. And omega is what we've been referring to as the angular frequency, which has units that we treat effectively as an inverse second. So notice this makes sense because amplitude is measured in meters, angular frequency is measured in an inverse second. Really, it's like a radian per second, but remember the radian is not like a real unit. And so we get meters times 1 over seconds, or meters per second. So that's it. The speed of a simple harmonic oscillator is a function of the position. When the position x, the distance from the equilibrium position, is 0, that's when the oscillator has its biggest speed, its maximum speed. And when x, the distance from the equilibrium position, is equal to the amplitude, then the speed is 0. That's it. Now, we've already derived this equation before, and by that I mean the next equation I'm about to talk about. But I want to just take a second to mention it again because it comes up in a lot of these problems with conservation of energy. Now, let's be clear. The thing I am about to talk about, it has nothing to do with conservation of energy per se, but in conservation of energy problems, they ask about it also. So I'm writing this under the heading maximum acceleration of a simple harmonic oscillator, SHO. So we can say here, if Fs equals negative kx, then that means writing it in terms of the amplitude, where the force is the biggest, would give us F equals Ka. Again, notice the only reason I'm replacing x with the amplitude is because the amplitude is the place where the x is biggest. We're trying to get an equation for the maximum acceleration. Hope it's clear to everybody that the maximum acceleration occurs when the force is biggest, and the force is biggest when x is biggest. And since x is the displacement from the equilibrium position, and amplitude is the maximum displacement from the equilibrium position, we replace it with a. Now notice I've gotten rid of the negative sign also. That's just because amplitude is a scalar, and so we're not going to go nuts. Now, the next important thing to realize is that that's the only force acting on the thing. And so we can write here Ka equals mass times acceleration. And I'm going to write max here because we're talking about the maximum acceleration. So that means A max equals Ka over m. Now, why am I talking about this when we already did it? Well, like I said, it comes up. But also, just notice I can rewrite it like this. And just very quickly to go back to the discussion we were having a second ago, if the frequency equation says this, which we can solve like this, and we said 2 pi f is equal to omega, then square root of k over m is equal to omega. So here, oh, it's just k over m, not the square root of k over m. How do I turn this to k over m? You see how you just have to square it? So we have omega squared equals k over m. And so we can rewrite that, let me just get rid of this, as omega squared times a. This part is not overly important, but it's a nice little pattern that can be shown with how these values, maximum position, maximum velocity, maximum acceleration, shake out. And I want to talk about that here before we take a look at a problem. Okay, so hopefully you picked up on that pattern there that we were discussing when we were talking about the maximum speed and the maximum acceleration, because notice what we see here is a very interesting little relationship. The position of the oscillator cycles back and forth between 0, and this is just a hypothetical example where the position happens to be 0 at time equals 0, to the amplitude, to 0 to the negative of the amplitude, to 0 to the amplitude, to 0. And it does this in a regular pattern. If it's at 0 at time equals 0, by the time it reaches one period, it goes through all of the possible positions, all the way up through all the positive ones to the amplitude, down through all the positives again, back down to 0, down through all the negative positions to the negative amplitude, and then back to 0. Look at what the velocity does. The velocity goes from a omega, or omega a, however you want to look at it, to 0, then to negative omega a, then to 0, then back and forth, always and always, just cycles back and forth between these values. Same thing for the acceleration, goes from 0 to negative a omega squared. Notice here it has the opposite sign of the position, to 0 to a omega squared to 0, back and forth and back and forth. This stuff is all about that conversion back and forth between potential and kinetic energy, causing these things to cycle, as we can see here in this chart. That's not overly important for the course, but it's just something that will sort of help you build a better understanding of how these systems work in general. All right, to finish us up for today, I want to take a look at this problem here in the simple harmonic motion packet. It's on page 11, number 18. This problem says an object spring system oscillates with an amplitude 3.5 centimeters. If the spring constant is 250 newtons per meter, the object has a mass of 0.50 kilograms. Determine the mechanical energy of the system, the maximum speed of the object, and the maximum acceleration of the object. Now, before we get into the actual solution of the problem, I want to talk very quickly about part A, because part A is a problem like we've never seen or at least discussed at this stage of the game. But it should strike all of you as fairly straightforward, I think. This is a problem where the object has its energy cycling back and forth between elastic potential energy and kinetic energy. And so there are a couple of ways we can think of the total energy in the system. We could, at any point, think of the total energy as the sum of elastic potential energy and kinetic energies. Whatever the elastic potential energy has to be at that position, whatever the kinetic energy happens to be at that position. Thinking about it in that way, though, in my opinion, is absolutely insane. Because there are parts in the motion, there are positions, essentially, where all of the energy is either just elastic potential energy or just kinetic energy. And so if I were you, I would think of calculating the total energy at a point where it's all elastic potential energy, in which case it would be the maximum elastic potential energy, or a place where it's all kinetic energy, and we're thinking about 1/2 times the mass times V max squared. Now, of course, the way you should do this, I think, depends on whatever information you're given in the problem. And so that's what I really want to talk about here as we go through this problem. Notice here they give us the amplitude of the oscillation. They tell us it's 3.5 centimeters. And so the first thing we'll write down then here for our knowns is the amplitude is 3.5 centimeters, which of course we're not going to use. We're going to use 0.035 meters. We have the spring constant K as 250 newtons per meter. And we have our mass here at 1/2 kilogram. We are asked, at least in part A, for the total energy in the system. Now, with the information we have here, we could determine the maximum speed. Notice that's part B. But since they already told us the amplitude, the smartest thing for us to do here, or at least the smartest thing in my opinion, would be to use the fact that the total energy is going to be equal to the amount of work we put in, which is going to be equal to 1/2 Ka squared. And so if you think about it like that, it's important to realize that this turns in to a pretty simple plug-in. We have 1/2 of 250 newtons per meter times 0.035 meters. And of course, we got to square that amplitude. And when you do that math, 1/2 of 250 newtons per meter times 0.035 meters, you end up with a total energy of 0.153 joules, which we can say is approximately equal to 0.15 joules. And that's it for part A. Now for part B, we're going to make use of another equation we talked about today, which is the equation for the maximum speed of the object. So B says, what is the maximum speed of the object? And as we saw here, you can determine the maximum speed of the object if you wanted to. You don't have to go nuts about this. First of all, we'll just write that V maxes are unknown. If you forget this equation, you can always bail yourself out by saying, well, the total energy in the system when the speed is maximum is going to be all kinetic energy. And so you could derive it yourself by setting 1/2 Ka squared equal to 1/2 mv final squared. And when you do that, you end up getting V equals the square root of K over m times a squared. And so that's what we'll start with. We'll say V max here is equal to the square root of K over m times a squared. And so I think it's a lot easier to use this equation, in my opinion, rather than putting something squared under a radical. It's just annoying to me. That at least is my personal opinion. So I'm going to take root K over m and just multiply it by a. And so I'm going to plug in here V max equals the square root of K, 250 newtons per meter, over the mass, which is 1/2 kilogram. I'm going to keep that all under the radical, and then I'm just going to multiply by the amplitude here, which is 0.035 meters. When you do that math, you end up here getting a number 0.7826 meters per second, which we can say is approximately equal to 0.78 meters per second. And so that's it for part B. Now, it should be noted, and we might as well just take a second to do this, that we in the beginning calculated the initial energy by using the equation 1/2 Ka squared, We could also, if you really wanted to, go back and use the equation 1/2 mv max squared to do that calculation as well. I think I mentioned this here in the beginning. If you use 1/2 v max squared, that'll work, or at least in theory, it should. And so if we take 1/2 of the mass, 0.5 kilograms, I know I'm squeezing this here in the corner very badly, and then we multiply it by 0.78 meters per second, and we make sure we square the whole thing. I know it's probably hard to see that. That's 1/2 of the mass, 0.5 kilograms, times v max squared. The speed we just calculated, 0.78 meters per second squared. When you plug that in, you do that calculation, you get 0.1521 joules, which we can round to 2 sig figs as 0.15 joules. Notice it works either way. The way you should do it in all these problems would be entirely dependent on whatever they give you, whatever makes it easier to handle. Now, we're going to have to go on to another slide here to answer part C. So take a second to pause this video here and write that down. And when you hit play, we'll move on to part C. All right, and very quickly here, let's just go to part C. Part C is asking us for the maximum acceleration of the object. Now, I mentioned this equation in this video again, even though this video had nothing to do with forces, because they love to mix these kind of questions. They ask you to calculate the maximum acceleration and the maximum speed, or the speed at any individual position at different points. And so I think that's an important thing to consider. And so here, we'll just go ahead and show this is an equation that you could just have memorized and write it down if you want. The equation is A max equals Ka over m. We talked about this already. But what I think is an important thing for you to remember is if you happen to forget that, you can always bail yourself out by remembering how to derive it. And that would be by setting the spring force equal to the net force and saying, well, Ka is going to be equal to m times the maximum acceleration. Of course, if you solve that for A max, you get Ka over m. And so here now, this I think is just a pretty simple plug-in. We have 250 newtons per meter times the amplitude here, which is 0.035 meters. And of course, we're going to divide that by the mass, 0.50 kilograms. And when you do that math here, making sure you have everything plugged in correctly, you get a maximum acceleration of 17.5 meters per second squared, which to 2 digits we can call 18 meters per second. And that's it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, and with that, that is it for today. Now, I know we spent a long part of this video talking about the bigger velocity equation, and that velocity equation is v equals the square root of k over m, I should say, times a squared minus x squared. And since this video is getting a little long here, and because the problem that I want to solve using that equation is quite long, we're going to call it a day here for now. That said, when we pick this back up tomorrow, we are going to go back through and use all of these equations again to solve a variety of problems, and hopefully that will make all this stuff a little easier for you to understand. All right, everybody, have a good one.